We're now going to go through a little bit of math, and right now we're only doing graphical math. So again, this is mostly a review from week 1. However, we are soon going to be getting to some component math, so it's important to have this correct. So the first thing is just basic addition. So if I have two vectors, E and D, we typically represent them starting at the same point. So in this case, their tails are starting at the same point. Now, if we want to add them, if you draw your sum in a vector when your picture looks like this, you're probably doing it wrong. I've seen many students look at this picture, draw an arrow, and it's probably going to be the wrong one. So what you want to do is take your second vector, in this case, E, and make it so that instead of starting here, the same place D did, it now starts over here. Now, I'm not very good at drawing, so luckily the book also gave us a figure where this was done. So this is just that red vector that I attempted to draw not so well. So the point is, we move it so that the tail of the second vector is at the tip of our first one, and then to get our sum, you start at the tail of your first vector and you draw to the tip of your second vector. So this is our sum here. So again, if you draw a triangle when your vectors are oriented this way, you have done it incorrectly. So what you want to make sure is that the second one is starting at the tip of your first vector. And if I gave you, for whatever reason, another vector, you could make that, going off in some direction here if this was G. And then if I wanted to say what is D plus E plus G, I would just again start at my starting point and then go to the tip of G. So you can actually do multiple vectors in a row this way, and as long as each one is starting at the tip of the previous one, you just start at the tail of the first one and go to the tip of the final one. Okay, there are two things to talk about here. First is just what does it mean to do scalar multiplication? And the idea of a scalar is that it has no direction, which means it isn't a vector. So in general, in this class, we will have vector quantities like a velocity or a force, and those have directions. Scalar quantities could just be like the number 2, or your age, or for instance, energy. Energy doesn't have a direction, so it's also a scalar. So that's the first thing. The second thing is to look at this notation. And the idea here is that when I have two quantities in parentheses like this, and this probably is familiar from your math class, this is your magnitude, which I can't spell, and then this is your angle. Now, something that I find is a challenge is to say angle with respect to what? Now in this case, it's horizontal, and normally this is going to be our positive x-hat direction, and so you can see that that's how the angle's been specified here. But in many physics situations, your angle needs to be something you say much more explicitly. So don't just write it as theta equals 30, tell me theta equals 30 degrees, where that is 30 degrees, in this case, clockwise from the positive x-hat direction. So that's just a little bit of notation, and frequently you won't be working in polar. Frequently you're going to be working in coordinates, which we'll talk about in the next video. But right now, what I wanted to focus on is the idea of scalar multiplication. So if I want to take my vector A is just this guy here, and multiply it by some constant, say 2. If I want to say, what does 2a equal to? Well, it's going to be twice as long, and it's going to have the same direction. So your direction does not change, but your magnitude does in kind of the obvious way, as long as we're talking about a positive scalar. And we'll talk, I think, next about what happens with a negative scalar. But so in this case, you can see that it's basically the same direction, but it's twice as long. So that's all that needs to happen for scalar multiplication. You just make the length scale by whatever factor, and that can be a number less than 1, like 0.5. Okay, so again, there's two things to talk about here. First is the idea of the zero vector, which we write as 0 with a vector sign over it. The zero vector doesn't really have a direction since it has 0 length, but the idea is if you have a situation like this where you're adding quantities together, every single one of them must be a vector. You can't really add a vector and a scalar. So I can add or subtract a 0 vector from another vector, even though it doesn't really have a direction. So it's a vector object that is equivalent to the number 0, but it actually is a vector. So that's the first thing. The second thing here is that if I say that I have some value, say x, and I'm adding a value to x to get 0, you know that I must have added negative x. So the same thing is true in vectors, that if I add my negative vector to itself, I get 0. And the only way that that will work is if I've completely reversed my direction, but I've gone the same length. So what your negative vector looks like is the same magnitude. So again, remember this means magnitude. So my magnitude hasn't changed, but my direction now, my angle, has effectively inverted itself, right? So this has changed. I don't know the best way to write that, but you actually just want to make it point back. So instead of pointing whatever angle from tail to tip, it's now anti-parallel, as you can see from tail to tip. So multiplying by -1 flips the direction. And again, don't think about, well, is that theta plus 180 or 360 minus theta? Don't worry about the math of it right now. Just think flips the direction, and otherwise that's the same. So hopefully that's clear. So combining the last two things together hopefully won't be that complicated, that if my initial vector has a certain direction and I multiply it by -2, this is like saying take A, my vector A, multiply it by -1, which flips the direction, and multiply it by 2, which makes it twice as long. And you can see that that's what the result is. Again, the fact that we're shifting this over on the page doesn't change the vector in any way whatsoever, so don't let that throw you off. But again, minus signs flip the direction, and otherwise it's just scalar multiplication. So the last thing to cover here is perhaps the trickiest, but again, you've seen this in chapter 1 and 2, so I'm hoping that it isn't brand new at this point, and that's the idea of vector subtraction. And there might be different ways to do this. The book actually shows 2. I know students sometimes claim they've learned other ways of doing it. I'm always going to use this method, which is to add a negative vector. And so what that means is that I initially have my 2 vectors starting from the same point. I want to create -c, and then I'm going to, remember, go from the base and then go to the tip, and then I'm going to add my vector there, which is a little challenging to draw. So this is my -c vector, and so then my sum, remember you want to start at the base of the first one and go to the tip of the second, that this then represents A plus -c. And so I've just done out all the steps, which this picture over here is showing you the answer as well. And again, the exact positioning here on the tip and getting the lengths right is kind of the difference between what I drew here and what you're shown here. But just please, this is the most straightforward way to do it. And the upside of this is that if you're always thinking about vector addition, you hopefully will have enough practice with vector addition that you do it right every single time. So vector addition is going to be something that comes up over and over and over again in this class because we're going to constantly work with vectors. So it's really important that you can add and subtract very comfortably in this graphical sort of manner. We're going to be talking about how to do it quantitatively in the next video. So just a quick summary, be careful about your notation. Things like having or not having a little arrow over top of your symbol actually makes a big difference in what someone thinks you're telling them. Scalar multiplication, oops, that's a typo, only changes magnitude. only changes magnitude. Multiplication by -1 flips the direction, and make sure that you're subtracting vectors by adding the negative.